Assalamualaikum warahmatullahi wabarakatuh. My name is Alia Binti Mohamad Zailani. Message number CE190192 from Group A514. For this MSKE session, I would like to present on power factor correction. This slide contains definition of power factor PF. What will we do for this activity? Connection of the system, expectation on PF after adding C capacitor, and conclusion on importance of power factor correction. Firstly, we have to know what is power factor. Power factor is an expression of energy efficiency. It is usually expressed as a percentage, and the lower the percentage, the less efficient power usage is. To be clear, the power factor is a ratio of an unit of AC electrical equipment or a whole electrical installation's useful real power kilowatt to its total apparent power kVA. The relationship between active, reactive, and apparent power is usually represented by a power triangle here. In addition, power factor expresses the ratio of true power used in a circuit to the apparent power delivered to the circuit. A 96% power factor demonstrates more efficiency than a 75% power factor. Power factor below 95% is considered inefficient in many regions.
Good day, doctor. I'm Tharnisha and my metric number is CE190099. So today I'm going to continue the presentation on the power factor correction laboratory session. So for this presentation, I'm going to present on what we have learned throughout the activity and also connection of the system. So first of all, in this activity, the main task was to learn regarding the power factor correction. First of all, the connection of the power factor unit was established. Next, we are required to calculate the reactive power P, which is equals to square root 3 VLIL cos theta, at where the line voltage of VL was set to 450 volt throughout the activity, while the IL varies for each and every step. Then we obtain the results for 5 different steps of L larger than R, at where L is the inductive load switches while R is the resistive load switches. Then the required VAR QC, which is also the capacitive reactive power compensation by using the formula QC equals to P times tangent theta 1 minus tangent theta 2, where tangent theta 1 is the up cost of power factor operating minus the tangent up cost power factor required, at where the operating power factor are less than 0.95 at each and every step, while the required power factor was larger than 0.95. Finally, we have to select the required steps by referring to a table in the next slide in order to achieve the desired power factor which is closer to the unity. So, this is the table I have done earlier. So, we can see we are using the last column of the table, which is the three phase for star connection, as the connections are in star. So, as referred to this table, these are the results we obtained. So, the results were obtained for 5 different steps, which is L larger than R, which is 1 refers to one number of switches, and number 2 is equals to 2 switches at inductive load, while 1 is referred to resistive load switches. So it goes like 3 for inductive switches, 4 for inductive load switches, while 5 inductive load switches. So as we can see here, throughout the activity, we can see that firstly L larger than R, which is 1 equals to 1. We got an IL of 3.5 and we obtained a power of 2138.43 watt for power factor of 0.85, while to achieve a desired power factor we required a VAR of 622.6 VAR in order to obtain the required power factor, while we choose step 1, which is nearer to 714.2. Next, secondly, for the 2 larger than 1, at where the IL is 4.2, the power factor given is 0.74, or the power operating power factor, and we obtained a power or reactive power of 2234.03 watt. So in order to achieve the desired power factor or expected power factor larger than 0.95 or closer to unity, we will obtain a required VAR QC of 1296.6 VAR. So the required step are step 2, which is closest to 1428.4 VAR. Next, for step 3, we have a IL of 4.9 and the operating power factor is 0.63. Then after calculation, we obtain a reactive power of 2218.94 watt, and the required VAR for obtaining a desired power factor was 2006.2 VAR, and it's required for step 3, which is nearer to 2141.6 VAR. Next, for the step 4, we have IL of 5.1 and power factor of 0.6. However, the reactive power is 2199.53, and we obtain a required VAR by the calculation, but it is 2209.4, and the required steps are step 3 also as previous. Then for step 4, which is 4 larger than 1, for greater than 1, we have an IL of 5.1, while the operating power factor is 0.6, and after calculating the reactive power, we obtain a power of 2199.53 watt, and in order to achieve the expected power factor, we will require a VAR or compensation reactive power of 2209.4, which is nearer to the last previous required step, which is step 3, which is 2141.6. Next, finally, for the step 5, we have IL of 5.9, which is having power factor of 0.56, which is the lowest power factor. Then we obtain a reactive power of 2374.92, and to obtain the expected power factor, we calculated the required compensation power, which is 2732.7 VAR, and the required step are step 4, which is nearer to 2856.8 VAR, in order to obtain the expected power factor. Next, let's look into the connection of the system. So, mainly in this power factor unit, we have 4 main components or devices, which is the main supply of 240 or 450 volt with 20 ampere current, and also main circuit breaker, digital measurement unit, analog measurement unit for taking the measurement of the power factor. So we have a 3-phase system, which is R, Y, and B. Firstly, 3 phases of RYB is connected to the main circuit breaker. Next, from the main circuit breaker, the yellow phase and red phase will connected to the analog measurement unit. Next, from the S1 at the main supply is connected to the S1 of the digital measurement unit, and from there S2 is connected to the S1 of the analog measurement unit. Then S2 from the main supply is connected to the S2 of the analog measurement unit. Next, the yellow phase and also blue phase are connected to the digital measurement unit from the main supply. Then these wires are connected to the outgoing of the main CB, while the red, yellow, and blue are connected respectively to the outgoing of the main circuit breaker. Next, we can see that this is the power factor panel, and also we can observe here that the blue phase are connected only at main supply to main circuit breaker and also the digital measurement unit, while red and yellow phase are connected between these four devices. So finally, for the first step, we will be measuring the operating power factor by only using the resistive loading unit and also inductive loading unit. So we can see here that there are four wires, which is red, yellow, blue, and also neutral. So the R phase is connected from a incoming resistive and also is connected parallel to the inductive, and it same goes to the yellow is connected to the resistive and also inductive, and blue connected to the resistive and also inductive. Then the neutrals are connected between each other of the A2, which is A2 to B2, B2 to C2, C2 again to A2 of the inductive loading, and also from A2 of the inductive loading unit we go to the B2, C2, and also uh, for the power factor correction, when we want to obtain the expected power factor, we will be adding the capacitive loading unit, and same by the parallel connection, we are connecting the red phase from the main going to the resistive, then also going to the inductive, then finally going to the capacitive. And same goes to the yellow phase going to the resistive, inductive, and also capacitive. Then for the blue also, if we go to the A1 of the resistive and connected to the inductive of A1, and also it connected to the capacitive loading unit. So what we can see is the neutral are connecting all the A2 switches, while the RYB is connected between the A1, B1, and C1. So that's all for the presentation of my part. So the next part will be continued by my group mate. Thank you.
Next, we continue to the expectation on power factor after adding C. The most common power factor correction device is the capacitor. In an AC circuit, magnetic reversal due to phase difference between current and voltage occurs 50 or 60 times per second. In addition, capacitor helps to improve the power factor by relieving the supply line of the reactive power. To be clear, the capacitor achieves this by storing the magnetic reversal energy. Capacitors can be installed at several points in the electrical system and will improve the power factor between the point of application and the power source. It is also can improve the power factor because the effects of capacitance are exactly opposite those of inductance. Capacitors are usually added at each piece of offending equipment, ahead of groups of motors, of motors control centers or distribution panels or at main service. Power factor correction is a technique which uses capacitors to reduce the reactive power component of an AC circuit in order to improve its efficiency and reduce current. It is also to reduce power consumption caused by heavier inductive load by balancing a motor's working power and supply power. The kVA rating of a capacitor shows how much reactive power the capacitor will supply. However, the power and the increased current draw between the load and the capacitor will remain unchanged. Last section would be importance of power factor correction. In conclusion, improving the power factor can maximize current carrying capacity, improve voltage to equipment, reduce power losses, and lower electric bills. The simplest way to improve power factor is to add power factor correction capacitors to the electrical system. Power factor correction capacitors act like reactive current generators. They help offset the non-working power used by inductive load, thereby improving the power factor. The interaction between power factor capacitors and specialized equipment such as variable speed drive (VSD) requires a well-designed system. Furthermore, power factor correction (PFC) aims to improve power factor and therefore power quality. It reduces the load on the electrical distribution system, increase energy efficiency, and reduce electricity costs. It also decreases the likelihood of instability and failure of equipment. The power factor correction will increase the load of the power factor and boost the efficiency of the distribution system. It will correct the linear load with a passive power factor correction capacitor. Also, the nonlinear load will deform the power drawn from the system. I think that's all for me. Thank you.